We'll start things off with NASA capturing images of what appears to be the strongest solar flare of the year so far.
Scientists say that this is just the beginning and warn of more severe consequences as the sun emits.
We often think of our sun as a gentle, reliable companion, a yellow constant that marks our days and seasons, nurturing every living thing below. But on occasion, this familiar star exposes a more turbulent nature. In recent weeks, NASA has issued critical alerts. After a relatively tranquil period, a potent sunspot has awakened and begun unleashing the year's most powerful solar flares. These warnings are not hypothetical. They are based on direct, real-time data delivered by NASA's Solar Dynamics Observatory, an instrument that continuously monitors the solar surface. On June 17, 2025, at 5:49 p.m. Eastern, a bright solar flare erupted, a blast so powerful that it was measured as the strongest flare recorded so far this year. Its energy immediately disturbed a spectrum of technologies on Earth, from communication satellites and GPS systems to terrestrial radio networks. As night descended, the geomagnetic effects translated into observable phenomena. Auroras stretched as far south as New Mexico, introducing new regions to a natural light show that most rarely see. This is not a mere weather report, but a significant solar geophysical event. Images captured by NASA identified the flare's origin as active region AR4087, a substantial sunspot now displaying complex, swirling magnetic activity. Far more than a surface blemish, AR4087 has acted as the epicenter for a series of X-class solar flares, bursts of radiation among the most powerful that our sun creates. Each of these outbursts is a direct communication from our star to our planet, conveyed across space in the form of electromagnetic and particle storms. With these events, crucial scientific questions emerge. Are we entering a period of increased solar activity? How will these cycles affect Earth's space weather and the systems we rely on? And as the energy from these flares continues to interact with our planet's environment, what should we expect next? Not just as spectacle, but as a test of our resilience and understanding. The Monster Awakens. NASA's Solar Dynamics Observatory is designed with vigilance as its primary goal, and the activity of recent days has tested that vigilance to its limits. In the Sun's northeastern quadrant, sunspot AR4087 has become prominent, exhibiting signs of high magnetic complexity. Observers first noted a cluster of darkened areas at the solar limb, which early analysis revealed to be the emergence of a new, magnetically potent sunspot. Rapid development followed. R4087's magnetic fields intensified and exhibited rapid motion, untangling, reconnecting, and releasing pent-up energy. These were not routine surges. The scale and suddenness were warning signs of the potential for X-class flares, the highest category of solar outburst. Early on Tuesday, May 14th, AR4087 produced a significant X7-class solar flare, a substantial burst that signaled escalating activity. Space-based sensors immediately recorded a sharp increase in energetic particles, and satellite operators initiated safety procedures to shield sensitive electronics. It became clear to NASA scientists that this was more than an isolated incident. It was a prolonged episode of solar unrest. Over the next weeks, the behavior of AR4087 grew more intense. Successive flares increased in both frequency and power. By mid-June, AR4087 was at its most active. On June 17th, the Solar Dynamics Observatory returned some of the most detailed available images of the flare event. Luminous arcs towering above the sunspot, eruptions of plasma that dwarfed the size of Earth itself. These moments, frozen in high-resolution imagery, provided insight into the underlying magnetic chaos driving the flares. The consequences extended to Earth. The June 17th event triggered shortwave radio blackouts across parts of Southeast Asia and Europe, with communication systems affected for minutes at a time. Aviation, maritime, and amateur radio operations experienced outages as bursts of solar radiation ionized the upper atmosphere, temporarily blocking key frequencies. Even systems on the sunlit side of Earth, including aircraft communications and navigation signals, registered disruptions, prompting urgent contingency actions. In space, further complications emerged. Alongside the flare, AR-4087 propelled a coronal mass ejection, CME, a vast bubble of plasma and magnetic fields on a trajectory toward Earth. These events, while moving slower than the initial flare, can incite geomagnetic storms when they interact with our planet's magnetosphere, and this particular CME was forecast to make a direct or near-direct impact. Every manifestation of stormy solar behavior in this period pointed back to a single source: the volatility of AR-4087, whose influence reverberated from NASA's monitoring stations down to the technological infrastructure and visible skies of Earth. What does this mean for the coming months, as AR-4087 continues its restless march across the Sun's surface? The answers may shape not only scientific forecasts, but the reliability of our daily technologies here on Earth. If you want to follow these solar storms and their unfolding impact, be sure to subscribe. Now, let's move on to what happened when Earth finally faced the brunt of AR-4087's power. When sunlight turns hostile. The flares originating from AR-4087 demonstrate that the energy radiating from our star can be both life-giving and occasionally disruptive. Solar flares travel at the speed of light, reaching Earth in just over 8 minutes. The electromagnetic pulse of such an event temporarily alters the electrical properties of the upper atmosphere, triggering radio blackouts and disrupting long-distance communications. On May 14th, the X7 class flare affected radio transmission across North America. Shortwave operators, radio users relying on frequencies between 3 and 30 megahertz, found their communications silenced as the ionosphere absorbed the energy, forcing aviation and maritime authorities to revert to backup communication protocols. Polar regions, which funnel solar energy more directly, experienced the strongest disruptions. The situation did not end with the passage of the electromagnetic pulse. The June 17th event was linked to a CME headed for Earth. By June 18th, geomagnetic storm conditions were observed as the bulk of solar plasma brushed past our planet. Instruments at ground level detected turbulent geomagnetic activity as proton levels surged, and dozens of satellites adjusted their configuration or entered safe mode to protect against the influx of charged particles. The most dramatic result, however, was visual. As the geomagnetic field responded to the onslaught of solar particles, auroras extended much farther south than usual. The northern and southern lights, mostly confined to polar regions, became visible over places such as New Mexico, an unusual latitude for such displays. Social media flooded with pictures from cities and rural locales alike, and people reported awe at seeing green, purple, and red bands ripple across the night sky. While scientifically fascinating, These events also spurred caution. Each major solar outburst has the potential to precede stronger episodes, and monitoring agencies remained on alert for further escalation. The anatomy of an X-class flare. For most, the Sun is synonymous with warmth and light, but observed through NASA's array of instruments, particularly those tuned to the ultraviolet and X-ray bands, the Sun is revealed as a boiling dynamic sphere where vast energies are stored and released. Solar flares are sorted into C, M, and X classes, with X class denoting the greatest energy output. An X1 flare is already capable of causing earthly disruptions, but an X7 class flare, like that which erupted from AR4087, is many times stronger, releasing energy on a scale difficult to produce or contain by human means. The trigger for these flares is magnetic reconnection, the rapid realignment of stressed solar magnetic fields that reorganizes energy and ejects it in a burst of light and charged particles. Each large flare liberates a quantity of energy equivalent to millions of nuclear bombs detonating simultaneously. The first impact is electromagnetic, but if a CME is associated, the event is extended, with the additional risk of geomagnetic effects once those charged particles reach Earth. The real threat to terrestrial systems is carried by these CMEs. As the high-speed plasma cloud collides with our protective magnetic shield, additional magnetic energy can be transferred to the magnetosphere. This may result in geomagnetically induced currents, GICS, electrical surges in power grids, pipelines, and even railways. Previous solar storms, such as the 1989 event that prompted the Quebec blackout, showcased how these space weather events can have terrestrial consequences. The link between sunspots, flares, and geomagnetic disruptions is clear, but the pattern of when and how a particular spot will produce such eruptions is still the subject of active research. AR4087's behavior stands out not just for its intensity, but for the sequence and frequency of its outbursts. Sunspots and the cycle of turmoil. Sunspots are temporary phenomena on the Sun's surface, visible as darkened regions where intense magnetic fields inhibit normal convective heat flow. Their appearance, size, and location follow an 11-year cycle known as the solar cycle, defined by increases and decreases in solar magnetic activity. The Sun is approaching or entering a solar maximum phase, the peak period of sunspot generation and increased flare activity. AR4087's appearance is consistent with the statistical trend of more and larger sunspots during maximum. However, the size and complexity of AR4087 set it apart. Its magnetic fields are particularly intertwined, creating conditions ripe for substantial solar flares. NASA's Solar Dynamics Observatory has supplied continuous updates, harnessing multiple imaging approaches to visualize the flux of plasma and magnetic forces above and around AR4087. These observations have informed not only the public, but the numerous industries and agencies with a stake in understanding and responding to space weather. After the intense June 17th and June 19th flares, the latter peaking at 7:50 p.m. Eastern, further reports of radio blackouts extended to parts of the Atlantic, with each energetic event matched by heightened monitoring. The process is not simply observational. Software suites and analytical models are deployed to anticipate the evolution of sunspot groups and the likelihood of future flares. Though sunspot behavior is influenced by underlying solar dynamo processes, not all cycles are identical. Some years, like 2025, may produce larger or more complex sunspot groups. Each cycle offers opportunities to improve predictive models, but uncertainties remain, both in short-term forecasting and in understanding how new sunspot regions, such as AR4202, observed on August 26, 2025, with an M1 flare, will contribute to the solar activity spectrum. Communication disrupted. Listening to solar fury. The global network of electromagnetic communication is susceptible to space weather, making solar flares and CMEs significant beyond the confines of theoretical physics. The major flares of 2025 have produced noticeable impacts. 5 continents reported radio blackouts as intense bursts of solar energy altered the ionosphere. On June 17th, frequencies in the 3 to 30 MHz shortwave band, critical for aviation and maritime operations, experienced temporary loss or degradation. Air traffic and shipping switched to contingency channels and backup protocols, emphasizing the need for redundant systems in an age of increasing reliance on radio and satellite communication. Satellite operators also confronted challenges. Many satellites are equipped with systems to detect and respond to increased levels of charged particle activity, entering safe modes to limit exposure and potential damage. Spaceborne infrastructure is inextricably linked to space weather, as these systems rely on precise, uninterrupted operation for navigation, climate monitoring, and communication. Everyday users felt the effects as well. Brief disruptions in satellite TV, GPS accuracy, and even localized cell network issues were reported as certain satellites temporarily reduced or altered operations to cope with the increased solar radiation. The most visible positive outcome for the public was the surprise appearance of vivid auroras in southern regions. Whether in the rural southwest United States or northern Europe, observers were treated to a spectacle that served as a visual manifestation of an otherwise invisible phenomenon. Scientists continued to map and analyze the sequence of events, noting the cascade of cause and effect from sunspot complexity to flare intensity to geomagnetic disruption. The focus was on learning not only how to predict such events more accurately, but also how to mitigate their impacts across essential infrastructure. Chains of causality, the solar domino effect. Major solar events occur as part of a linked sequence. An X-class flare can disrupt radio signals seconds after it is released. A CME reaches Earth a day or more later, imposing an additional, sometimes more severe, geomagnetic impact. As these charged particles encounter the magnetosphere, they can enhance or disturb local magnetic fields, with consequential effects on power grids, navigational systems, and ground-based sensors. Geomagnetically induced currents, generated by rapid magnetic field shifts, have caused historical blackouts, and in this cycle, similar risks were under review as geomagnetic readings climbed. Satellite operators manage spacecraft safety by reorienting or temporarily powering down certain components. The International Space Station has procedures for heightened radiation, including adjustments in orientation and activity protocols. On the ground, utilities monitored their networks for anomalous current surges, especially in higher latitude regions where natural geomagnetic transmission is stronger. Warnings and watchful eyes, NASA's alerts. The network of agencies and experts monitoring solar activity coordinates closely during major events. NASA, as the leading U.S. space science agency, disseminates solar storm alerts to partner institutions, governments, and industries relaying information from the Solar Dynamics Observatory and other space and ground-based assets. The recent sequence of events has prompted elevated bulletins and reinforced the value of multifaceted observation and forecasting. NASA's alerts have informed grid operators, aviation regulators, telecommunications providers, and public agencies, emphasizing the value of early warning systems in reducing risk. Past events, like the 2003 Halloween storms, the 1989 Quebec blackout, and the 1859 Carrington event, serve as sobering reminders of what is possible when geomagnetic storms reach massive scales. While the recent sequence has not matched those historical extremes, the pattern of repeated powerful flares and CMEs from AR 4087 triggered comparisons and sustained vigilance. New sunspot regions continue to develop, as with AR 4202 in late August, which produced an M1.0 class flare, ensuring persistent activity as solar maximum continues. The rhythm of warnings and monitoring efforts has become familiar, but the inherent unpredictability of space weather keeps the scientific community alert. The infrastructure of vigilance comprises technical protocols and public awareness. For critical personnel, it means checking redundancy and executing contingency plans. For the general public, it is a reminder of our dependence on the sun's stability and the advances in science that let us foresee and respond to these cosmic events. The mystery persists. As the latest series of flares ease and new sunspot groups begin to appear, researchers are left with enduring questions. Each sunspot, flare, and CME adds to a growing understanding of solar physics, but also highlights the limitations of our predictive power. AR 4087 will eventually move across and out of sight on the solar disk, its impact trailing in the currents of the upper atmosphere and the data lines of technology. Its legacy will be written in scientific publications, operational reviews of affected industries, aurora photographs, and continued refinements of the models predicting space weather. The recurring challenge is to tease out why certain sunspots, like AR 4087, grow so large and active, and what particular magnetic configurations most reliably lead to significant flares. As new observations accumulate, patterns may emerge and predictive skills may improve. But the sun remains a complex and fundamentally dynamic system. The lesson from this period is clear. Our connection to the sun is both intimate and dependent, subject to vast forces that we are only beginning to appreciate in full. Every major flare, every episode of geomagnetic disturbance is a practical reminder of our ongoing relationship with the star at the center of our solar system. If a single sunspot can initiate global phenomena, in technology, in skies, in scientific knowledge, then understanding and anticipating the sun's rhythms will remain a priority, both for practical safety and for the fundamental questions of science. Look up. Each aurora, each brief disruption in telecommunications is a nudge to remember our world's exposure to the sun's dramatic behavior. The story of solar storms continues to unfold, shaped by cycles yet to be completed and depths yet to be plumbed. As new sunspots arrive on the solar disk, stay attentive to scientific updates. They are our window into the ongoing story of how space weather shapes our lives. The next chapter is always just over the sun's horizon, where data, curiosity, and vigilance combine in our continuing quest to know and coexist with the universe's forces. Stay watchful. Our world depends on it.